Alright, we're going to set up Fc of m is equal to Fg of m between the two masses. So Fc of m here is just going to be equal to m Vm squared over r, which is distance from the center of mass from one of the masses, which is equal to G m over distance between them is the two masses 2r, and then we square that, then we can start combining. So we have, so I can cancel this m, so we have Vm squared is equal to Gmr over 4r squared, and these r's cancel out, and then so we're left with Gm over 4r. Now we just square root them, and so the whole thing, see, so you get Vm is equal to square root of Gm over 4r meters a second, and that will be the speed of one of the orbiting masses. For part B, we're going to set up Vm is equal to 2 pi r in this case, which is because that's the radius of one of the orbits, of the orbit of one of the masses, all over pt, which we're trying to find. And so what I can do here is move t over, so it'll be t is equal to 2 pi r over Vm. And then I could just plug in the velocity here, because this coincides with this, because this Vm is equal to 2 pi over t, and you just plug in here, so it's just t is equal to 2 pi r over square root of, make this bigger, square root of Gm over 4r. And then you could flip it, so now you have 2 pi r times the square root of 4r all over radical Gm, which is just equal to 2 pi times the square root of 4r cubed, because then r is just square root of 4r squared, all over rad Gm, and that'll be the period, and this will be in seconds. See, we're going to find E total, which in this case is going to be the Ke of one of the masses plus the other Ke of the other mass minus the gravitational potential energy, so I'm going to put Ug, and then we can start plugging in. So this is equal to 1/2 times the mass times Vm squared, and this one is also, Kem is also, the other one is 1/2 Vm squared, because they're the same mass, minus the gravitational potential energy was Gm times m all over the distance between the two masses, which is 2r. And then what we remember earlier, Vm squared, if you ignore the radical here, is going to be equal to Gm over 4r. So Vm squared is Gm over 4r. So then we can set this equal to 1/2 of m times Gm over 4r plus 1/2 m times Gm over 4r minus Gm squared over 2r. And now what we notice here is that these two combine together, so since they're the same one here, so it's 1/2 of this whole thing. So now we could combine this, as since it's 1/2 of Gm squared over 4r, it'll be, and there's two of them, so it's just Gm squared over 4r, which is the combined kinetic energies, minus the gravitational potential energy, which is Gm squared over 2r, and that's just going to equal to negative Gm squared over 4r, which is going to be in joules. Okay, so for the angular momentum of the system, we're going to combine both the angular momentums of the masses, so it will be Lm plus Lm, which we know is just, since they're the same mass, they're going to have the same angular momentum, so it would be 2Lm. And then for now, I'm going to leave out the direction, so I can because I know they're going in the same direction, but I'll put in the n. So we LM. So it's 2 times m. And then if we look here, VM for each one of them is going to be perpendicular to the radius no matter where it is. So even if it's up here, R will be like this, and VM will be going perpendicular to it. So then it will be VM times R times VM is 2L cis, so it's 2mr VR. And now we could simplify that, so 2mr, and we could plug in what we got earlier for V, which is square root of gm over 4r. And now we could start putting combining the rest, putting it all into this easier, a much better form. So we know 2 squared is 4, so we square root of 4 times m squared, because m times r squared g all over 4r. So when you simplify this, you'll get radical gm cubed times r, and in this case, because of the way it was oriented, it will be gm cubed r kg m squared over s, and then it was going in a clockwise motion, and that'll be your angular momentum. So now we're going to find the xcm. We'll find a new center of mass to start drawing off the diagram. So first I'm going to find the distance away from the center of mass from the 3m. So x of 3m, cm from 3m is equal to, well, we have 3m, and that's 0. I'm going to use 3m as a reference, and that's 0. It's exactly on it, so I don't have to worry about it. And then for the regular m, we know that the distance between the two stars still is 2r, and this is all over 3m plus m, and so the m's cancel out, and we're left with 2r over 4, or r over 2, which means the center mass is r over 2 away from the 3m, and since we know the distance is 2r, so it's xcm of m, so that means we just take 2r minus xcm of 3m, which we know is just 2r minus r over 2, which means that we get 3r over 2 as its distance of the center from the object with mass m. We're going to start off with the center mass, which is going to be right here, which is going to be cm. And next up, we're going to start drawing the orbit of each orbit. So I'm going to start with here. So it's going to be the 3m mass. So I'm going to put it about here, and the orbit will look like, the circular orbit will look like this, approximately if this was like a beautiful circle. And next up, I'm going to set up so we know this here is going to be r over 2, and then next up is the m, so we know it's going to be 3r over 2 away, so I'm going to put it over here, and this is 3r over 2, and then once again we're going to draw a circle, so then it's going to look like massive compared to it. That's because so then the circular orbit will be like this, and so we know this is going to be 3 over 2, because then this is a smaller mass, so then it's far away from the center mass then compared to the 3m, and so this is roughly what a circular orbit will look like with scaling approximate, because then this one is each r over 2 represents half an inch, so it's triple the radius of this. And so that's the circular orbit of this new system. Alright, for the angular speed of 3m, we're going to set up fc of 3m, and that's going to be fg. And fg of 3m with m, so then this is going to be, I'm going to use omega, so we 3m times omega 3m squared times the distance from the center of mass, which in this case is r over 2. And that's going to be equal to g times 3m times m all over 2r squared. So now we can start isolating for this, we start crossing out. So this 3m cancels this 3m, and now we can start moving it over. So it's going to be omega 3m squared is equal to this. I'm going to multiply 2 divided by r, so it'll be 2gm over, this is 4r squared. So now this is going to become 4r cubed, and then this becomes a half. So this 2 over 4 is just 1/2. So I'm going to change this to half. Then we square roots the whole thing. And now we have omega 3m is equal to square root of gm over 2r cubed rads a second. And that'll be the omega for the 3m. So to compare the orbital periods between them, I'm first going to set up FC so I can find the period. So this FC of m is equal to f of g of m, which is going to be the same as f of g of 3m. So we m times omega m squared, and this is r is distance from the center is 3r over 2. That's equal to gm times 3m over 2r squared, and then this m cancels with this m, and I can start moving stuff. So times 2 divided by 3r, so the omega m squared is equal to g2g, and it's 3 cancels this 3, so we m all over 4, and this r goes down this denominator, and this is a rate r squared, so it'll be 4r cubed is equal to omega m squared. So it's omega m to be square rooted the whole thing. You have omega m is equal to square root of 2g, or in this case it would be gm over 2 r cubed. What we notice is that omega m here is the same, this is the same as this one. So what we know is that omega m is equal to omega 3m, because they're the exact same value here. And then if you set up, so omega in this case for m here is 2 pi over tm, and this is 2 pi over t3m, which represents the period. And then we multiply both sides by t3m and tm divided by 2m. So we notice is that t3m to tm, because then these cancel out, and then we flip it. So now we have t3m is equal to tm. So that means the periods are going to be, even though this is a greater mass, has a greater mass, 3m has a greater mass, the period is the exact same as the smaller mass. For part H, to find the new orbital period, I'm going to set up new orbital period. So omega m is equal to 2 pi over tm, or in this case I need to leave it as t, and this omega is going to stay the same so as the 3m. So even if we use the omega 3m, it's going to be the same thing. So this is rad, so omega we know is rad gm over 2r cubed to 2 pi over t. And if we multiply by t and divide by omega here, we get t is equal to, so we have 2 pi as still, and that's radical of, so this flips, so it's 2r cubed all over gm. And if we compare that to the previous period, which is here, which is 2 pi rad 4r cubed over gm seconds, so this should be seconds right here. Well, we notice that this is bigger than this one, and so this t, so this new t is going to be smaller than the previous one, so I'm going to put it as t2, and this one has t1 as before. And so, in this case, t1 is greater than t2, so that means the new orbital period decrease. So next part, we're going to set up the ratio, so that we have v3m all over vm. And now this is going to be equal to just, v, and this v is going to be equal to omega, and this is omega 3m times the distance from the center, which is 3r, which is just r over 2, all over omega m times 3r over 2. These omegas are the same, so they cancel. The numerator has r over 2, as does the denominator, so the r over 2's cancel. So now we're left with just 1 over 3 as a ratio of 1 v3m over vm. Okay, so for j, we're trying to find a ratio of L3m, which is the angular momentum of 3m, over the angular momentum of m. And so we're going to use a similar method. So we're going to set up MVR in this case. So in this case, it's 3m times v3m all over times the distance from the center, which is perpendicular distance, which is r over 2. And this is all over, going to be over, let me fix this, m, angular momentum of m, which is m times vm times 3r over 2. So once you set this up, we notice here that this v3m vm we found earlier is just going to be what we found, which is 1/3. And so we can start simplifying stuff. So now this m and this m cancel. This r half cancels this r half. And so this 3 and 3, because they both have this, is present in the numerator and denominator. So now we're just left with v3m over vm. And in this case, v3 over vm, we found earlier, it's just 1/3. It's the ratio between angular momentum of 3m over angular momentum of m. It's just 1/3 again. Okay, next for k, what we're going to do is we're trying to find the ratio between L3m over L system. And we know L3m, in this case, I'm going to use I, so it'll be I of 3m times omega, because they have the same omega for each part of the system. In this case, an L system here will be I 3m times omega plus I m times omega. The omegas cancel, so now we just expand the moment inertia. So in this case, it's going to be, so this I right here will be 3m with mass, and since it's a plan, we're going to treat its c value as just 1 times r over 2 squared all over 3m times r over 2 squared plus the I of this one, which is going to be m times 3r over 2 squared. And now we can start simplifying. So this m cancels out. So now we have 3, this is r squared over 4, all over, this is also 3, r squared all over 4, plus here it's 3r squared, 3r, and that square is 9r squared all over 4. And then you can cancel out this 4, this 4 here, this r squared, this r squared over 4, this r squared over 4, and this r squared over 4. So now you're left with just 3 over 3 plus 5, which is 12, and then your ratio would now be 1/4. Okay, so now we're going to do K, ratio of kinetic energy of m all over kinetic energy of the 3m planet. And so we can set up as 1/2 m is vm squared over 1/2 3m times v3m squared. So I'm just going to convert, so I'm first going to cancel out this 1/2 m and this 1/2 m because they're same. And then, so now we have just vm squared over 3 v3m squared. Let me rewrite this meter. 3 vm squared. Now I'm going to rewrite this as vm, so you know it's v is equal to omega r. So vm here will be omega squared times r squared, which is 3r over 2 squared. This is all over 3 times omega squared again for vm. And this is going to be, and the r here will be r over 2 squared. And so now we can start canceling, so this omega squared cancels out. And now we have 9 r squared over 4 is all over 3r squared over 4. This 4, r squared over 4 cancels out. Now we're left with just 9 over 3. And so our final ratio for Km over K3m is just 3.